we will see the module 12.3 where we are starting the colloidal state. Thomas Graham was the first scientist who observed substances behaving in two different ways. For example, sodium chloride when dissolved in water, we get sodium chloride solution. That solution, when allowed to pass through parchment paper, the solution readily diffuses to other side. Not only water solvent, with it the sodium ions and chloride ions also freely move to the other side of the parchment paper. But when the solution of glue or gelatin, it is allowed through parchment paper, the rate of diffusion is very slow, and gelatin or glue particles, they don't readily go through the parchment paper. That is, the solution of glue or gelatin, it is very slow in its diffusion, whereas the solution of sodium chloride, its rate of diffusion is very high. From this, Thomas Graham at the first stage concluded there are two types of substances in solids, like sodium chloride, the solutions of which are readily diffusing through parchment paper, and solutions of glue-like substances which diffuse through parchment paper or animal bladder very slowly. To explain them in a clear manner, he called substances like sodium chloride, which are allowing their solutions to freely pass through, as crystalloids, and the substances like glue, gelatin, they are called colloids. In that way, at the first instance, Thomas Graham felt there are two different substances like colloids and then crystalloids. However, after thorough observations by other scientists as well as Thomas Graham, all these scientists concluded that the behavior of the solutions, it is not two different types of substances like crystalloids and colloids, but the glue-like substances, they have only difference in sizes of their particles in the solution compared to those of crystalloids. Because these substances like glue have bigger size for their molecules in the solution, these particles are not diffusing fast or their rate of diffusion is slow. Therefore, compared to crystalloids, these colloids, they have only difference in the sizes of particles, not they are two different substances. That is why later on they said these are not two different types of substances, but they are two different states of substances like gaseous state, liquid state and solid state. Substances will have for their particles one more state based on the sizes of their particles, and this type we can call them as colloidal state. In that way, the colloidal state was introduced. Colloidal state is very important, not colloids as different substances. In a way to clearly understand this, let us see what are true solutions, what are suspensions, and what are colloidal solutions. Sodium chloride, for example, or sugar, for example, when dissolved in water, any one of them, it forms a clear solution. And this clear solution, when it is filtered, the solution clearly comes through filter paper. Types of substances like sodium chloride, potassium chloride, or potassium chromate, these we can call them as the substances giving true solutions which are homogeneous, that is same concentration throughout. Whereas if we dissolve barium sulfate in water, barium sulfate will not distribute itself to give uniform solution in the water. The substance directly goes down because of gravity to the bottom of the test tube. Barium sulfate, even clay you take, these substances which don't give homogeneous solution but simply don't dissolve and settle at the bottom of the test tube containing water due to gravity, we call them as suspensions. That is our precipitates you can keep in mind to understand suspensions easily. Now, you take glue solution, or in the labs you will be observing aluminum hydroxide precipitate, aluminum hydroxide. These, they neither give true solutions like sodium chloride, nor give precipitates or otherwise suspensions like barium sulfate. The particles are in between, and you find the solution as if it is a glue solution or gum-like solution. These solutions, we call them as colloidal solutions because the solute particles are in a different size, bigger than those in true solutions and smaller than those in suspensions. And to understand this three types of substances, that is true solutions, colloidal solutions, and suspensions, let us see some properties of these three solutions. Here, we have classified property, suspension, colloidal solution, true solution. That is, properties of these three states we will be seeing. What are those three states? Suspension, colloidal solution, and a true solution. Here, first point regarding the property, we will see particle size. What is the particle size we observe here? For suspensions, it is greater than 100 nanometers. Nanometer means 10 to the power of minus 9 meter. Therefore, here particle size is greater than 10 to the power of 100 nanometers, means relatively bigger in size, whereas in true solution like that of sodium chloride, the particle sizes will be less than 1 nanometer, means almost 100 times less in size, or more than 100 times, you can understand. Whereas the third state just we are discussing now, it is colloidal solution. For colloidal solution, the particle size is 1 nanometer to 100 nanometers. Do you understand the difference? Here true solution is with particle size less than 1 nanometer, whereas in suspension the particle size is greater than 100 nanometers, whereas in colloidal solution it is in between, that is 1 nanometer to 100 nanometers. In that way, based on the particle size, you can clearly classify the three states of matter in solution as suspension, colloidal solution, and a true solution. Then, separation by 1. Ordinary filtration. Generally in the labs, when you get precipitates, you filter the solutions. For example, while going for group separations, we do this. When you do separation by ordinary filter paper, here ordinary filtration can easily separate the suspension from the solvent or solution remaining. Therefore, the precipitate or suspension you can get on the filter paper. Whereas colloidal solution, it is not possible with ordinary filter paper to separate it. And true solution also, you cannot get the solute, that is the substance dissolved, separated from the solvent. Ultrafiltration, that is using some special type of filters known as ultrafilters. Compared to ordinary filters, ultrafilters will have very fine pores, small pores. Then, even when you use ultrafiltration, this is possible. Suspension can be easily separated. Whereas colloidal solution also can be separated. That is, the substance present in the solution can be the one which gives colloidal solution. It can be separated on ultrafilter. Whereas true solution, even now, even when we use ultrafilters, it is not possible to separate. Means the particles of solute as well as solvent, this even go through the ultrafilter. That is how you can see, while separating, ordinary filtration can be easily separating suspension, but not, these two are not possible. Ultrafiltration, it can separate suspension as well as colloidal solution, but true solution, it cannot be separated into its components. Now, what about the settling of particles? Settle under gravity. What does it mean? Simply, if you allow the test tube in which the suspension is formed to settle to stand like that for some time, the substance in that will be readily going to the bottom of the test tube because of gravitational force. In that way, suspensions, they can allow their particles to settle under gravity. Whereas colloidal solutions, they don't settle so easily under gravity because the particles are so small. And however, if you allow the colloidal solution to undergo centrifugation, then under centrifugation, colloidal particles may settle down. Means these colloidal solutions allow their particles to settle under centrifugation. Now, true solution, they don't even allow the particles to settle, the solute particles to settle even after centrifugation. In that way, we can understand settling of particles very easy in case of suspension because gravity itself will help us, whereas for colloidal solution, extra energy we must use, that is centrifugation we have to apply, whereas here even centrifugation also fails to settle the particles. Then, appearance to the naked eye. If a precipitate is there in a test tube or suspension is there, can you see through the suspension the other side of that glass test tube containing suspension in its solution? No. That means the suspension is opaque. You can understand it is opaque. Whereas colloidal solutions, they are generally transparent. Means through colloidal particles, because they are relatively smaller in size, the other side can be seen when the colloidal solution is in a glass test tube. Therefore, they are generally transparent. True solutions, however, you know, they are clear and you can easily see the other side, means they are fully transparent. Means regarding their appearance, these are opaque, that is suspensions, and colloidal solutions generally transparent. If however bigger sizes are there, then there may be some difficulty, but true solutions clearly transparent. Then diffusion of particles. Here the solute particles don't diffuse in precipitates, they settle at the bottom. Only solvent particles, they start diffusing from top to bottom in the test tube or from bottom to top, but suspension will not allow its particles to diffuse. You can observe with barium sulfate precipitate or lead chromate precipitate in the lab, that precipitate will not move when you allow it to settle to the bottom. However, true solutions, you don't find any difference between the solvent particles and solute particles. Both will simultaneously diffuse, and rate of diffusion also will be very high in the case of true solutions. In this way, you will have a classification between three states of matter, that is suspension, colloidal state, and the third one, true solutions. Here you understand one thing. The one minimum, if you take for a colloidal solution, that is required condition, minimum there are two components in a colloidal solution. One will be in large amount, the other will be in small amount. The large amount will be in a continuous manner, whereas the small amount will be in a discontinuous manner. For example, if you see glue in water, what will happen is glue particles, they will be in a discontinuous manner, whereas water is in continuous manner. The one which is in continuous manner, it is called dispersion medium, or because it is external, we call it as external medium, dispersion medium or external medium. Whereas the glue particles you consider, they are called dispersed phase. Dispersion medium, dispersed phase. Or because those particles are inside the solution, you can also call that as internal medium. Internal medium. In that way, you can see colloidal solutions will have one dispersion medium, the continuous one, whereas the other dispersed phase, which is a discontinuous phase. Note that colloidal solutions need not be always the dispersion medium, the liquid, whereas dispersed phase is solid. Colloidal particles can be of three states: gaseous state, liquid state, and solid state. And dispersion medium also can be of three types, that is solid state, liquid state, and gaseous state. We will see some examples for different types of solutions, because based on the state of the colloidal particle as well as the dispersion medium, based on the states of these two, we have different types of colloidal solutions. Let us see that. We will see the different types of colloidal systems taking dispersed phase in three states, that is gaseous state, liquid state, and solid state, and dispersion medium that also taking in gaseous state, liquid state, and solid state. Here, if we go one by one, dispersed phase, let us take it as liquid, and dispersion medium, gas. Means the one which is in relatively small amount is liquid, the one which is relatively in more amount, it is gas. The colloidal system, it has a special name when the dispersed phase is liquid and dispersion medium is gas, and it is called aerosol. Aerosol of liquids, because the dispersed phase is liquid. Aerosol is regarding the dispersion medium when it is gas. Therefore, here aerosol of liquids. We see number of examples in our daily life. For example, fogs, clouds. What are these? In all these, even mists, all these, they contain water vapor dispersed in air. A cloud, what is a cloud? It is nothing but water vapor settled in air. In that way, liquid is water vapor or water in the liquid form, and dispersion medium is air. In that way, aerosol we get for liquid dispersion phase, it is fog, cloud, mist, etc. Then solid, gas. What do you mean by it? The dispersed phase is solid and dispersion medium is gas. Because this is solid, dispersed phase is solid, we can call them as aerosol of solids. Aerosol of liquids you have seen, now we are seeing aerosol of solids. Example, smoke. What difference do you find between fog and smoke? In fog, water liquid is dispersed, whereas in smoke, dust particles, they are dispersed in gases. Whereas volcanic dust also is an example for this, and haze, where dust particles you can see mixed up with air. Therefore, these examples give the dispersed phase as solid and dispersion medium as gas. In general, when dispersion medium is gas, you call it as aerosol, and if the dispersed phase is liquid, it is aerosol of liquids. If it is solid, it is aerosol of solids. Then this is gas, that is dispersed phase is gas and dispersion medium is liquid. Example is, best example you can have, soap lather. The colloidal system is named as foam or froth, and examples for this is soap lather, foam, whipped ice cream. Here, to your naked eye, clearly soap lather you can understand in liquid the air dispersed. Similarly, foam, where air is dispersed in liquid, and whipped ice cream also you will contain some liquid, some gas dispersed in liquid. Whereas both are liquids. For example, take water and add to it oil and shake, then what you get is emulsion. The name of the colloidal system is emulsion. And examples of emulsions are emulsified oils, milk, and some medicines where oils are dispersed in water. You get medicines also existing in colloidal state. In that way, emulsions are with the dispersed phase in liquid phase and dispersion medium in liquid phase. That is how we get some examples here. Here, let us take dispersed phase as solid, that is solid state, dispersion medium as in liquid state, and colloidal system at that time is called sol. Solid, dispersed phase, liquid, dispersion medium, and due to that, if a colloidal system is formed, it is called sol. What are the examples? The paints we observe, they are examples for this. You must be seeing the paint, it is a best example for a solid getting dispersed in a liquid. Starch in water. If you dissolve in hot water some starch, you will not get clear transparent solution, but the starch distributes in a colloidal state in water. Therefore, starch in water. Proteins, gold salt, arsenic sulfide salt, even your ink contains in liquid dispersion medium a solid dispersed phase distributed. In that way, some examples you have for salts containing dispersed phase as solid and dispersion medium as liquid. Then dispersed phase as gas, dispersion medium as solid. This is called solid foam. When dispersion medium is solid and dispersed phase is gas, the colloidal system is named as solid foam. Best example is pumice stone and styrene rubber and foam rubber, or otherwise you can find foam beds. There rubber beds, rubber material will be there, solid material, in that air would be distributed. In that way, dispersed phase is gas, dispersion medium is solid. Therefore, these are the examples for that type. Then dispersed phase is liquid and dispersion medium is solid means the corresponding substances you call them as gels. Solid is in excess and liquid is in small amount. That is why you call that state as gel. Gel is the name given for the dispersed phase in liquid state, dispersion medium in solid state. Examples: cheese, butter. Every day you are seeing in your daily life butter. Even boot polish in the solid state, that is dispersion medium, a liquid is dispersed. That's why boot polish also is an example for dispersed phase in liquid state and dispersion medium in solid state. Jelly, China grass for example, and even your curd also will give an example for this type. Then the last one, solid in dispersed phase, solid in dispersion medium, then you call them as solid salts. Example: ruby glass, some gemstones, and also alloys. They give homogeneous solutions, alloys give two solids combined together. You can take them if the component particles are in the size of colloidal state. We can call that substance as colloidal system, and therefore both are solids means you can call that as solid salt. And here examples are given as ruby glass, some gemstones, and alloys. Okay, now if you carefully observe, so far we observe only 8 solutions or 8 colloidal systems, whereas if solid in 3 phases, that is dispersion medium in 3 phases and dispersed phase in 3 phases, if these combinations are totally put, you should get 9 types of colloidal solutions, whereas we are so far seeing only 8 types of solution. What about the 9th? 9th one should contain dispersed phase as gas, dispersion medium as gas. That type of colloidal system never occurs. Why? If both are gases, they have totally independent rates of diffusions, that is, rate of diffusion is very high, and they don't contain particles of colloidal state. Therefore, two gases, when they combine, they can never form a colloidal system. That is why our colloidal systems are limited only to 8. Therefore, we don't get 9 types of colloidal systems. We have seen the first classification of colloidal systems based on the physical state of either dispersed medium or dispersion medium, dispersed phase or dispersion medium. In that way, 8 types of colloidal systems we got. Next classification we can make regarding colloidal systems is with respect to the attraction between the particles of dispersed phase and the particles of dispersion medium. If dispersion medium has affinity or attraction towards dispersed phase, then we say the colloidal system is lyophilic. Lyo means solvent, philic means attraction. That is, if dispersed phase allows its particles to be attracted by dispersion medium particles, it is lyophilic colloidal system. If colloidal particles, that is dispersed phase particles, are not attracted by dispersion medium particles, then automatically we will call it as lyophobic systems. Lyo means solvent, phobic means repulsion. In that way means no attraction. In that way we have, on the basis of the attraction between dispersed phase particles and dispersion medium particles, two types of colloidal systems known as lyophilic systems and lyophobic systems. If the solvent is water, that is dispersion medium is water, then we call it as hydrophilic system. Hydro from water. And the other one is hydrophobic system. Now, here let us see the differences between lyophilic salts and lyophobic salts in their properties. First of all, let us take some examples for lyophilic salts, otherwise known as suspensionoids, and lyophobic salts, otherwise known as emulsionoids. Examples for lyophilic salts are our gum solution and gelatin, starch, proteins, rubber. Whereas lyophobic salts are metals like Ag, Au, hydroxides like AlOH thrice, FeOH thrice, and sulfides like arsenic sulfide, that is As2S3. In that way, you can see lyophobic salts and lyophilic salts. Now, what about their properties? One, surface tension. Generally, if it is a lyophilic salt, what is it? Lyophilic salt, then the surface tension decreases, because that is, the colloidal system will have lower surface tension than the medium alone if you take. That is, starch solution will have less surface tension than pure water. Whereas lyophobic, because the solvent particles are not affected by the dispersed phase particles, here the surface tension of the solvent, that is water, for example, here if you take whether it is pure water or in the colloidal system, it maintains the same surface tension. Reversibility, these are easily reversible. For example, you can make a colloidal solution of starch, but if you evaporate the solution, the solvent simply goes away, leaving starch in the solid state. These are irreversible generally. Relatively, compared to these are irreversible, because there are no forces of attractions between solvent particles, that is dispersion medium particles, and dispersed phase particles. It is in no way affecting the separation of those components. That is why once this is formed, it is not normally possible to reverse the process. We can understand. Stability. Lyophilic salts are more stable because there is always attraction between the dispersion medium particles and dispersed phase particles, whereas here the stability is relatively less. Visibility. The lyophilic salts are such they are not even seen under ultra microscopes, whereas this can be easily detected under ultra microscopes. Ultra microscopes are special type of microscopes. migration. These lyophilic salts, without any charge on the on the particles of dispersed phase, they can migrate in any direction, but not under electric field due to no charge on their particles. That is, dispersed phase particles don't independently carry any charge. They are heavily hydrated or solvated. Due to that, they can move in any direction, whereas lyophobic salts, their particles are dispersed phase particles are charged particles, and they move under electric field only, either to cathode, that is negative electrode if they carry positive charge, or to anode, that is positive electrode if they carry negative charge. In that way, based on the charges on the colloidal particles, their migration would be decided. Then, action of an electrolyte. Suppose a small amount of an electrolyte you add. Then, small amount of an electrolyte when added to lyophilic salts, it makes no effect, no difference, because already lyophilic salts are heavily solvated or heavily hydrated if the solvent is water. Therefore, a small amount of electrolyte cannot make any effect here, whereas a small amount of electrolyte on addition will precipitate or coagulate here the lyophobic salts. Then hydration, because here these are solvent attracting dispersed phases, highly solvated, or if the solvent is water, highly hydrated. Whereas here there is no attraction between dispersed phased particles and dispersion medium particles. That is why there is no question of any hydration. In that way, based on attraction between the colloidal particles of dispersed phase and the dispersion medium particles, because of attraction and no attraction, you can divide them as lyophilic salts, which have attraction of solvent particles on colloidal particles, and lyophobic salts, which have no attraction on colloidal particles from the solvent particles or dispersion medium particles, into two types. This is the second classification. We have seen till now two types of classifications of colloidal systems. One is on the basis of the physical states of colloidal system, that is based on the physical state of dispersed medium, dispersed phase, and then dispersion medium. The second one on the basis of the attraction between the dispersion medium particles and dispersed phase particles. Now the third classification we are seeing here on the types of particles. Third type of classification on the types of particles. Here the first classification we get as multimolecular colloids. For example, gold, silver, sulfur, etc., take them in their fine powdered form, that is in atomic state we can get them. When they are obtained in atomic state, then we dissolve in a particular solvent acting as dispersion medium. What happens is these particles, almost in atomic or molecular states, they get aggregated to colloidal state almost to less than 1 nanometer size. When they come to less than 1 nanometer size almost, they are colloidal particles. And the attractions between the solvent particles, that is dispersion medium particles, and these colloidal particles are purely van der Waals forces of attraction. Therefore, this type of colloidal systems where individual atoms or molecules aggregate together to the colloidal size, we call them as multimolecular colloids. that is number of atoms or molecules combining and giving colloidal particles. Example, silver, gold, sulfur, etc. Because here the van der Waals forces attract and the dispersed phase particles are less than 1 nanometer size, mostly these colloidal systems, they are lyophobic. They are not attracted by particularly solvent like water. Then macromolecular colloids is the second classification. Really, starch, cellulose, proteins, enzymes, etc., they are very big in their sizes. Those particles, when put in water or any other suitable solvent, they get dissociated or they get separated into such molecular size which are around less than 1 nanometer, that is colloidal particle size. Here, when bigger molecules get split into colloidal state, macromolecular, because they are obtained from macromolecular state to colloidal state, we call them as macromolecular colloids. Whereas these are multimolecular colloids, because simple molecules add together and give colloidal particles. These are also from bigger molecules we get colloidal particles. This is second type, and these are mostly lyophilic, that is solvent attracting. Why? Because they are macromolecules, bigger molecules, they have to be split up into smaller particles, means solvent also must help for it. Therefore, there must be attraction between the dispersion medium particles and dispersed phase particles. Therefore, this is lyophilic. Then there is third classification with respect to types of particles. For example, these substances, that is third type substances, if they are taken in very low concentrations, they behave like exactly normal electrolytes. That is, they give true solutions. But when the concentration is more, what happens is these particles aggregate together and come to the colloidal size. When they come to colloidal size, you get colloidal particles, and automatically this is because of association of component particles. We call this colloidal state as associated colloidal state, and in the associated state the particles are called micelles, and this we will discuss in the next part. Here, in this way, we have on the types of particles multiple molecular colloids, macromolecular colloids, and associated colloids. Multimolecular colloids means from independent atoms or molecules we get colloidal particles due to their association, and macromolecular colloids means from very big aggregates of component particles, they can be split and brought into colloidal state. And associated colloids means normal electrolytes. They are generally normal electrolytes. At low concentration, they are giving true solution, but when the concentration is increased, they aggregate together, that is dispersed phase particles aggregate together and come into colloidal state. That is how this is associated colloidal state we get, and we call these as micelles in the colloidal state.